In 2000, the UK's Engineering and Physical Sciences Research Council launched 5 computer-centric interdisciplinary research collaborations, or IRCs. 2 of these, the Advanced Knowledge Technologies IRC and Medical Images and Signals IRC, have joined forces via the UK's eScience funding initiative. The Medical Imaging and Advanced Knowledge Technologies project, or MIAKT, aims to provide semantically enriched service-based support to the breast cancer screening programme. MIAKT is a 2-year research collaboration involving the universities of Southampton, Sheffield, Oxford, the Open University and King's College London. MIAKT combines leading-edge research from knowledge technologies and image analysis and is building upon the ambitions of the semantic web, where data on the web is explicitly defined and linked in a semantic network that allows its meaning to be interpreted by machines. MIAKT is at the forefront of exploiting ontologies for the composition of a significant number of services in a semantically principled way. The breast cancer screening programme in the UK and the USA makes it mandatory for women over the age of 50 years to undergo breast cancer screening. NHS guidelines require the assessment of cases to be undertaken in collaborative meetings where medical staff with expertise in the reading of different case-related data come to a mutual decision on the treatment given to the patient involved. This meeting is known as the Multidisciplinary Meeting, or MDM, and typically involves a radiologist to interpret the X-ray mammograms, a pathologist to interpret pathological images, and a clinician who will have information on the patient's history. To store knowledge from various medical staff, a formal taxonomy of functional nomenclature is created based on the type of knowledge that needs to be stored. This is called the domain ontology and has been created using semantic web technologies. The MIAKT architecture is a distributed system where relevant algorithms and functionality are made available through various forms of web service to a server that makes them available to a roving client application. For example, image analysis functionality is provided by sites that have both the relevant expertise and computational power. The middleware enterprise server makes these web services available based on an ontological description we call the application ontology. The user interface is provided by, but not limited to, a client-side applet that is accessed through any Java-enabled web browser. Security to the interface is currently provided through username and password databases which link available applications to a user. Once the user has logged in, the architecture is populated to the specification of the selected application, as described in its application ontology. Once the application client is visible, 2 different views of the domain ontology are presented. The tree view displays the subsumption hierarchy of the domain ontology, and a graph view presents all relationships between concepts in this ontology. Through these views, it is possible to bring up definitions of the concepts in the domain ontology to clarify the nomenclature used. It is also possible to get instances of certain concepts. For example, listing instances of the patient concept gives us a list of all the patients in our system. Prior to an MDM taking place, the relevant experts will examine a patient's case information and identify points to discuss at the meeting. Selecting a patient from the list will bring up all the information known about that patient. For instance, the patient shown here had an X-ray mammogram taken on the 15th of October 1992, of which the images are displayed here. As fits with well-known traditions, the underlined blue writing represents hyperlinks to other instances in the domain ontology. For example, clicking on the link for an image retrieves more information about that image, including that in this case, a region of interest has already been identified within it. If we return to the patient case, we can see that a report of the patient's history has been automatically generated using natural language techniques that intelligently convert the underlying RDF representation into natural language. This is one of the web services that is made available to the client through the middleware server, and in this case was executed in the University of Sheffield, where the technique was developed. This type of labour-saving service could be used to save medical staff the time and expense of having to write patient reports by hand. The middleware also allows mapping of specific domain concepts to input parameters of web service method calls. This allows automatic delivery of service methods to the client user interface, providing fast application prototyping. For example, this drop-down list shows all the services that take a patient as input. If we select a service and click Invoke, the service will be executed with the current patient instance as the input parameter. This particular service is being called at the Open University, where their Internet Reasoning service is providing these simple case retrieval services to MIAKT. Normally, as a patient progresses through the course of their treatment, their case is discussed at more than one MDM. All the patient's major events are shown along the interactive timeline, and the detailed information about all the events are shown in the patient information window. Better views of images in the patient's information can be brought up by clicking on them. The viewer can be used for inspecting and annotating the images. Images are delivered from the relevant image servers directly to the client, avoiding clogging of the middleware server with large amounts of data. X-ray images are delivered using the Internet Imaging Protocol, which provides a means for downloading areas of high-resolution images on demand using tiling. The viewer also allows annotations to be created on the image using established methods. When an annotation is created, the client's generic framework automatically sends the annotation's low-level description to feature modules, which have registered themselves to receive that type of low-level descriptor. Feature modules can be local or remote to the client. Remote image analysis modules are accessed through a defined web service API, and features associated with the images are stored in feature vector databases at the remote site. Results from any algorithms are returned in this list and can be asserted into the knowledge base here. This patient has also had magnetic resonance imaging, MRI. MRIs are constructed like a stack of regular images to give a three-dimensional view of the breast. It can be very useful to find differences between MRIs that were taken at different times or after a lesion enhancement substance has been injected into the tissue. However, movement in the patient can cause the images to be misaligned. Image registration manipulates the images so that they are aligned on top of each other and can be subtracted to find differences. We can invoke a registration by selecting the images we wish to align and clicking the Register button. This is a highly computational task, and the algorithm developed at King's College London uses a cluster of computers over the grid to achieve this. When the registration is complete, the newly constructed image will be asserted into the knowledge base. MRIs can be inspected and annotated using a special MRI viewer. Like the X-rays, MRIs are delivered from institutional image servers directly to the client. Once the MRI has been transferred, annotations can be made on any of the slices within the MRI. As with the X-rays, image analysis modules that understand an MRI annotation's low-level descriptor will be called. This image analysis module, developed in King's College London, has classified the lesion from a training set to suggest that this lesion is malignant. Well-known classification algorithms such as naive Bayes are easily invoked through the service-based architecture. For example, this region of interest has some features associated with it, and using these we can attempt to classify whether it is malignant or benign based on patient data for previous cases. You can see that the classifier classifies this as a malignant lesion, which matches to the outcome we have stored for this patient. Currently, the MIAKT system is a proof of concept, but could be of value immediately as an information management system. In the UK, the real benefits will accrue when digital imaging of mammograms is more common. We expect to take the work forward in the medical domain to deliver better image processing and reasoning tools. The distributed nature of the system's resources means that it has the potential to be integrated with current hospital information systems, like the Picture Archiving Communication System, or PACS, and patient record systems. There remain substantial issues in the deployment of systems like MIAKT. These have as much to do with social and ethical considerations as any technological impediments. In the UK, there are strict rules about how patient data can be communicated and used. What MIAKT powerfully demonstrates is that via ontologies and adopting a semantic web approach, heterogeneous, complex information can be integrated, annotated, and services deployed in collaborative decision support contexts. Finally, MIAKT's generic architecture means that the system could be ported to other multimedia knowledge management applications with ease.